Hello and welcome. It's SFU Math 152. My name is Brenda Davison. This is section 7.3, Trigonometric Substitution. So this is a useful method for certain types of integrals that are typically involving the square root function. I'm not going to put a huge amount of emphasis on this. You should know about it. You should know how to do a basic one, but I don't think it's that valuable to spend lots of time on this particular tactic. So it's a little bit more of a minor topic than some of the other ones. Substitution itself, major importance. Integration by parts, major importance. And then the other main tactic that we're going to see is going to be partial fractions. That's a really important one. This one is sort of a little bit of an offshoot of the regular substitution and is of lesser importance, but we will go through and see what we get out of this slightly new tool. Okay, let us take a look at a problem that we may have. Here we have an integral, square root of a squared minus x squared dx, and we have a picture of that function right there. And right now, we don't know how to evaluate this integral and get some function. Now, were I to add endpoints onto here, for example, I made this from minus a to a, those specific endpoints, in fact, then we would see that this integral, the definite integral now that I've added those limits of integration, would be this area here, and we see that that's half of a circle of area 2. So we would know that this is pi a squared over 2. Let us say, though, that we had wanted to do the original indefinite integral. Okay, so then we need to come up with some function whose derivative is this function here. Now, maybe the obvious thing to try, I would be thinking from what I've done before, maybe try letting u be equal to a squared minus x squared. That won't work because the problem is then what would happen is we would end up with du equals minus 2x dx. And the problem is we have dx here, but there is no x here. So we would find it difficult to get anywhere with this kind of substitution. So that doesn't work. And this is our normal way that we have been substituting, where we have our new variable, u. So this is how our previous substitutions have looked like. We've had our new variable, in which we've often used u, and it's been set equal to some function of our old variable, which has often been x. So we would have often set u equal to some function of x, which is what we tried here. U equal to some function of x. In this case, the function of x that we're talking about is a squared minus x squared. And what we're going to do with this this type of substitution is we're going to do we're going to call an inverse substitution, which means our new variable we'll actually put x equal our old variable equal to a function of our new variable. We're going to see how that happens. Okay, so first of all, just before we go into an example which will serve to illuminate this idea, we are going to notice that if our integral has this type of structure, a squared minus u squared. Now notice u is my old variable. Then I'm going to substitute u, and this is going to be my new variable. But what I actually have here is my old variable is a function of my new variable. And then coupled with this substitution, we will find we need the knowledge of this trig identity. Okay, and then similarly, if we see this kind of a structure, we're going to use this kind of a substitution, and we're going to use this identity, etc. So there's 3 cases outlined here, and we're going to go through a couple of examples and see how this works. So let's take our first example. That will be the integral of the square root of 1 minus x squared. Okay, so and that's assuming that the absolute value of x is less than 1. That's so we don't get a negative underneath that square root. Okay, so now what we're going to do is a different type of substitution. We're going to substitute in this manner x, that's our original variable, x, and we are going to make the substitution x equals sine theta. So our new variable is over here on this side, and our old variable is over here. That is opposite to what we have been doing before. So that's sort of the big idea. And just pointing out in the table that I have above, this is the case where in my table I am on the first case. Just let me roll back here to see how. So this is like sort of, I labeled these 1, 2, 3, situation 1, 2, and 3. I'm in situation 1 with a equals to 1. That's where I'm at. Okay, so my substitution is going to be x equals sine theta. That means that dx equals cosine theta d theta. And in fact, it means that theta equals the arc sine of x. And 2 theta, why am I doing this? You'll see in a sec, will be 2 arc sine of x. And then let me just draw a triangle according to this substitution. I have this substitution, x equals sine theta. So I put theta here, and the sine of theta is opposite over hypotenuse. So this is x, and this is 1. And then this is square root of 1 minus x squared. Now there should be some light for that sort of thing. Oh, alert, right? I'm now seeing, in fact, something that's also sitting right here. Maybe start to see how this is going to come together. Okay, so I have a triangle like that. I have a substitution. I've just written down some facts here. Okay, now let's see what's going to happen here. I want to do this integral here, the square root of 1 minus x squared dx. And I have to make a complete substitution like I always do. And so I'm going to substitute in this way, 1 minus, and what is x? X is sine theta. So x squared is sine squared theta. And then what is dx? Okay, so I have substituted for x, and I've substituted for dx. dx is cos theta d theta. So this becomes cos theta d theta, like that. Now I use the associated identity in the table, and I will have this as the square root of cos squared theta, cos theta d theta. So this cos squared theta is 1 minus sine squared theta. And then I can proceed along these lines, and then that will be the square root of cos squared will be cosine theta. So then cosine theta times cosine theta is cos squared theta d theta. And then I can do this, we've already seen this. So now we've reduced this problem to something that we can already do, and we use the double angle identity. So we write this like this, 1 plus cos 2 theta over 2 d theta. Then I can integrate each one of those, and I get 1/2 theta plus sine 2 theta over 2 plus a constant. Now we have to do the back substitution. The back substituting is harder when you're doing these kind of things because we have to back substitute and get this back in terms of x. That's what we started with. We want a function of x. And we know that theta here is the arc sine. Okay, so we figured that out. We however, don't actually know what is sine 2 theta yet. I mean, we know that x is sine theta, but we don't know what sine 2 theta is. So the next thing I'm going to do is write this like this, 1/2. Okay, I do know what theta is in terms of x, is the arc sine of x. And what do I know about sine 2 theta? Well, sine 2 theta is 2 sine theta cos theta, and that's still over 2. Okay, that is the identity, the double angle identity, sine 2 theta, 2 sine theta cos theta, and then I've still got the constant, and then I'm still trying to move in pieces here to get the whole thing in terms of a function of x. So that I've already done with that. Those 2's will cancel out. Now I've got sine theta and cos theta. Well, I know what sine theta is. Sine theta is x, because that's my substitution. And then what is cos theta? And that is when I'm going to refer to this triangle here. This triangle tells me here's my theta, and then I have all 3 sides of it's a right angle triangle. I have all 3 sides, so I can get all 6 trigonometric functions from that. And looking at that, I see that cos theta is square root of 1 minus x squared, and then we still have our constant. Okay, that's done. So that is our result there. I'm just going to put a box around that. Okay, there it is. That is the answer to the original integral. You can see that this one, I think, is the complexity is a little bit higher. The substitution is inverse to what we had done before, and then you have to have an associated identity, and then we also had to use two other identities when going through, and then the back substituting was more complicated. So these things are definitely a little bit more involved, take a little bit more time and consideration, but what you should have in your mind is this is sort of already been detailed out for you what the correct way to approach that is, and that is basically see this, do this, and use this. You know, see this, use this, and use this. So it is at least there's some guidance here about what to do. Okay, let's look at a slightly more complicated example where you have to maneuver a little bit to get it into the form that you need to use one of those three things in the table above. Okay, so I am going to take this and I am going to multiply top and bottom by 1/16. So I'm just going to even have that inside the integral sign there. And we'll see in a sec, I hope, why that is the case. And that is 4x squared plus 9 all squared. The reason for it is because I want a 1 here. I want it to be x squared plus a squared so that I can see what type of substitution I should make. Okay, and if I multiply top and bottom by 1, I don't change anything. And then now that allows me to put this 1/16 in the denominator. I'm going to move that inside here, taking the square root when I do that. So then this will be 1/16. That is the 1/16 in the numerator. Then it will be dx, and I'll be moving the 1/16 into this under the square, and so that I have to take the square root when I do that. This is algebra. Careful algebra, like that. Maybe stop at each one of these steps and assure yourself that you understand the steps that I'm making to do that. And so then I'm going to further move this in here like that. So this will become 1/16. Then this will be the integral of dx over x squared plus 9/4 squared. And one more step here to see it exactly the form that I need. The integral of dx over 3/2 squared plus x squared squared. Okay, there's no coefficient in front of the x. So that was the reasoning behind this bunch of algebra. So I haven't done any integrating really at all. All I've done is algebraically manipulate the integrand so that you'll notice there's no coefficient in front of the x. Okay, and then so now what we have, it is, by it I'm referring to the integrand. It is of type a squared plus u squared. So I have something that's squared plus the variable squared. That is the type that it is. So I can then now see what substitution I should make, and that substitution is as follows then. I look at the table and I think, okay, I will be substituting. Let x equal 3/2 tan theta. Okay, so I need to make a complete substitution, like always, and my dx then will be 3/2 secant squared theta d theta. And I'm also, because I've looked at the table, or I recall from when I've previously done this, I'm thinking of this identity is going to be used. Okay. Let's go ahead then and make that substitution. This becomes equal to 1/16, and then the integral will be, let's look in the numerator, we have dx. So dx is going to be replaced by 3/2 secant squared theta d theta. And then let's look in the denominator. The denominator will be, let me think here. It is x is 3/2. So x is 3/2 tan theta. So I have here 3/2 squared plus x squared. That's going to be 3/2 tan theta squared, and there's a square there. Okay, I got to then factor out this 3/2 here. Okay, I see the, maybe put a color here. So then now I'm back into doing some algebra. So I'm going to factor this 3/2. There's a 3/2 squared sitting there, and then that it's also itself squared. So there's a 3/2 squared on both of these, and then there's a square here that gives me 3/2 to the 4, and then there's also a 3/2 in the numerator. So I'm going to get all those numbers together. So I'm looking at here having still that 3/2 in the numerator, secant squared theta d theta, and in the denominator I'm having 3/2 to the 4, and then I have 1 plus tangent squared theta there also, and that is squared. Okay, I can then get I've got 3/2 divided by 3/2 to the 4th. That is going to be 2/3 cubed. So that is 2/3 cubed. And then we still have I'm just moving that outside the integral, all those numbers outside the integral. I have secant squared here in the numerator, and in the denominator, 1 plus tangent squared is secant squared. I got secant squared squared. So this is d theta over secant squared theta. And that is then 1/16 times 2/3 cubed times the integral of cosine squared theta d theta. Now we're in a position, we're in fact in exactly the same position we were in the previous example. We now need to evaluate cosine squared theta. And let me just remind you what is theta. Or what is, okay, I'm looking now at the triangle corresponding to the substitution. I know that the tangent of theta is 3/2. Sorry, I know that the tangent of theta, let me try that again. Okay, now that I said it wrong, I'm going to say it again. 3/2 tangent theta is x. So that means that the tangent of theta is 2x over 3. Okay, this is a substitution. That thing there matches this thing here. It's just is written slightly differently. Okay, that's the substitution. So I draw a triangle that represents that, and I put my theta here, the right angle triangle. I know the tangent is 2x over 3. Opposite over adjacent must be 2x over 3, and that of course allows me, using the Pythagorean theorem, to calculate this thing here as 4x squared plus 9. Now I'm just going to point something to you. You notice this came back in some sense. you see that the hypotenuse of this triangle is indeed 4x squared plus 9. That is a major clue that you haven't flubbed up any algebra. So this is often going to happen. You're going to be working through doing a whole bunch of maneuvering around, and then as you're sort of getting closer to the end, you're like, okay, there is that thing that was in the integrand originally kind of re-showing up. That is a very good sign. Okay, now I'm going to integrate cosine squared, which I've already done twice. So I'm going to do that in one step, and I'm also going to simplify this numeric expression right here. I mean, 16 is 2 to the 4. So I have 2 to the 3 in the denominator and 2 to the 4 in the numerator. That's going to give me 1 over 2, and then 3 to the 3. Okay, that's 2 cubed divided by 2 to the 4. And I'm making a note to myself there. Okay, and then I'm integrating the cosine squared, which is going to be 1/2 theta plus sine 2 theta over 2 plus the constant. And then I keep going. I know what is sine 2 theta. That is 2 sine theta cos theta. So, and I can also combine this half with that. Now I'm here 1 over 2 squared 3 cubed. like that, and I do the back substitution. What is theta? Well, I know that the tangent of theta is 2x over 3, so theta is the arctangent of 2x over 3. I'm going to have to move my triangle up here. Theta 2x over 3 square root of 4x squared plus 9. That is the triangle. I'm going to get rid of this so I have a bit more space. Okay, so I've got the 2x over 3, and then I need sine 2 theta over 2, which is 2 sine theta cos theta over 2, which is just sine theta over cos theta. So what is sine theta? Sine theta is, let's see, sine theta is opposite over hypotenuse. That is 2x over square root of 4x squared plus 9. And then cosine theta, which is adjacent over hypotenuse, which is 3 over that same square root. So why don't I just do that in one step and make that 4x squared plus 9. So that right here, that's a times. This right here is sine theta times cos theta. I highly advise you at this point to stop the video and go through each one of these steps, assuring yourself that you can follow each step. So it's much more complicated, and particularly this back substitution, you have to be cautious. I always have to draw the triangle. You have to be considering which identities you're using. Again, we've used 3 trigonometric identities in going through this procedure here. That is the final answer. Right there, that last bit here. This is the final answer. Original integral. There it is. Okay, next example. We're looking at square root of x squared minus 25, and there's an x in the denominator. That does not help us to make it a like when I would first see this, where we're not in the context of this lecture, I might be thinking to myself, oh, am I going to just do this because I see this? But that is in the denominator. So were that to be in the numerator, this would be a good idea, but this is in the denominator, so this in fact does not turn out to be useful. At this point, at a minimum, at this point, what should have occurred to you is that integration is a much more difficult, orders of magnitude more difficult problem than differentiation. Okay, there's a lot of different tactics and it's not algorithmic in the same way that differentiation is, and to make it algorithmic requires a lot of high power tools. So what we're doing is developing some what we would call a heuristic method. You're sort of using your experience, you're looking at it, you're trying things. I'm not going to emphasize on trying to do really difficult integrals. On the other hand, be aware like that this is a significantly more difficult a problem, and for that reason, in fact, it's also a more interesting problem. Okay, so I'm looking at this one. I see that it is of the form square root of x squared minus a squared, where a is equal to 5. There's no coefficient in front of the x, so I'm going to make the substitution x equals 5 secant theta. And that will mean that dx is equal to 5 secant theta tan theta d theta. And I'm going to be coming into my head right now is that this identity is going to be important. Okay, I can say it either way. Tan squared plus 1 is equal to secant squared. Okay, and let's see what else. Maybe also thinking that the derivative with respect to theta of tan theta is secant theta. Maybe just have that little fact sitting there as well. Okay, so let's see if at this point we can make the substitution. We know that x is 5 secant theta, and we've computed what is dx. So the integral of the square root of x squared minus 25 over x dx is equal, I'm going to substitute all parts, so x squared minus 25, well, x is 5 secant theta, so this will be the square root, and x is 5 secant theta, and that's going to be squared, that's x squared, minus 25. And then what is x? X is 5 secant theta. That's nice. And then what is dx? Dx is 5 secant theta tan theta d theta. Looks a bit awful, but things are going to get good really quick. First thing that we're going to notice is that we can easily factor out a 5 in the numerator, so all of these things are going to go away. 5, that is 5 squared is factored out and take the square root, so that is gone, and that is that will become 1. So then I've got secant squared minus 1 in the numerator. Secant squared minus 1 is tan squared. Let's just go here. So now I've got simplifying that underneath the square root there, that is going to be, move this 5 out here, 5, that's that 5, and then this one here, and then I'm thinking secant squared theta minus 1, and I take the square root of that, and it's going to rewrite that as tan squared theta. And then in the denominator, I have this secant theta canceling with that secant theta, and I have an additional tan theta here, and then I have the d theta. And so things get nice now because the square root of the tangent squared is the tangent, so this becomes 5 times the integral of tangent squared theta d theta. Okay, now I'm going to use the identity again. So this is going to be 5 times the integral. Tangent squared is secant squared theta minus 1 d theta. And I did that because I know which function has derivative secant theta. That is the tangent. So that now allows me to integrate. So this is now at this, going from this step to the next step is saying, how do I integrate the tangent squared? And I'm saying that the way to do that is to use the identity here. And then because you already can do by inspection the integral of the secant squared. So this then becomes 5 times, now I'm actually performing the integration, tan theta minus theta plus a constant. Okay, now it's the back substitution. We need this in terms of x. So I'm doing the back substitution. So what do I have? I'll just, now that I'm on that part of the program here, what do I have? I have that, well, given the substitution that I used, I know that secant theta is x over 5. And I'm recalling then that secant theta is 1 over cos theta. So then I know that I'm thinking then, okay, so I see that this is hypotenuse over adjacent. That is going to allow me to draw that triangle. And I'm going to need for the back substitution. So here we have theta. I know that the secant is x over 5, and that is the hypotenuse over the adjacent. And then that allows me to calculate this side here, the height, and that is x squared minus 5 squared. And the same thing happened. This x squared minus 5 squared now has shown up here in this special triangle. And I feel happy when I see that happen, because it leads me to believe that I haven't lost something along the way, which, as you can see, is pretty easy to do. Okay, so we're on the back substitution. This is what I am trying to substitute. So I'm saying here 5 tan theta minus theta plus c is equal to 5 times tangent of theta. What is the tangent of theta? Well, I look, it's opposite over adjacent, so that is the square root of x squared minus 5 over 5. And then what is theta? Okay, we know that the what is theta is, I'm looking at my triangle. Theta is, I can pick actually more than one here, but I'm looking at the simplest case here, these two things. And I'm like, okay, I'm writing theta as the arc cos of 5 over x. I mean, theta is also the arc sine of, you know, for example, the arc sine of square root 5 x squared minus 5 squared over x. But the arc cos is simpler here. And there's a constant. Okay, so that the thinking behind this here is that secant theta is x over 5. My substitution, cosine theta is 5 over x. So therefore, theta is the arc cos of 5 over x. That's the thinking there. Okay, and that, in fact, I can do a little bit of simplifying. So my original integral, which I was trying to compute, the integral of the square root of x squared minus 25 over x dx, has now been found to be, this will cancel here with that 5, and then I'll have to multiply the 5 in over to here. So I'm going to get here square root of x squared minus 25 minus 5 arc cos 5 over x plus c. The final answer. Okay, trigonometric substitution. Gotta love it. And let's take actually a look at, I think, something more interesting, a problem. So the problem is what is interesting about the problem is setting it up. And like I've said before, it'll be the case in our examinations that some of the integrals, some of the problems, the exam problems will be, you know, set up, but do not evaluate the integral to do something. And then you go ahead and set up the integral, and then you're done. So we will, in this case, set up this integral, and I will think what I'll do is I'll set the integral up. I will tell you what type of substitution to use, and then I will tell you the answer. And then it'll be good news for you, good work for you to go through, actually try the substitution. You've just seen 3 examples. Try the substitution and go through and make sure that you can get the answer. And in fact, if you want to challenge yourself right now, might be a good idea to stop the video and try to set up the integral yourself and see whether you get the integral that calculates what's being asked here. Okay, so we've got a water storage tank. It's a right circular cylinder with diameter 10 feet. It's placed so that the circular cross sections are vertical. The depth of the water is 7 feet. What percentage of the total capacity is being used? Okay, so let's draw this out. It's a right circular cylinder, diameter 10 feet. And it's tipped on its side. So the cross sections, if you like, so the circular cross sections are vertical. So this is what I'm reading here. We've got a right circular cylinder. There it is. And the vertical cross sections are circles, and the diameter is 10 feet. So that means 10 feet is from here to here. So that would mean, for example, I'm just going to draw a line through the center here. This height, of course, then would be 5 feet, the radius. And it's got water in it. It's not full. The depth of the water is 7 feet. Okay, so I'm going to draw the water with a little bit of a ripply surface. Not that the water has a ripply surface, but just to sort of indicate it's the water. So this is the water here. This is the water in the tank. It's like that. And this distance right here is 7 feet. Okay, and we want to know what percentage of the tank is being used. Okay, first of all, as a practical thing, what you could say to yourself is like, you know what, were I able to lift this, if I just turned it upright, if you want to look at upright as being that way, if I turned it so that the circular cross sections were horizontal, it would be a much easier problem. Okay, but you see those oak barrels aging wine, they're sitting on their sides like this, and you want to know how much are being used. Okay, so we want to think of this as slicing up something somehow and having slices of the same shape so that we can add them up. Seems a bit daunting. So whenever there's an issue like this, I think, what can I do first? Okay, I know I'm going to have to calculate the total capacities. I mean, the percentage that's being used. That means I'm going to have to know what the total capacity is. That's an easy calculation. Let me do that so I can get rolling. Okay, so let's do that calculation. Total capacity. Sort of try to make it sound possibly like a joke, but honestly, if you've got a problem, you think, oh no, I'm not sure what to do, then just do whatever you can do. If it's the most basic calculation, just go ahead and do that, and get yourself starting to at least find out some things. Okay, so this is the total capacity is the volume of the cylinder. And that total volume is pi r squared h, the volume of a cylinder. So that is pi. We've identified what r is. And then h is the length of this thing. Pi r squared h. What is h? Does not specified. I was just momentarily stopping, thinking here I was going to make a simple calculation. Now I seem to be stymied. H is what I'm, in the way I've written my formula. H is this distance right here. When I was trying to calculate the total capacity, and then I was thinking, I don't know that, but so that's fine. So I'm just going to leave it like that. So that's then going to be 25 times pi times h. 25 pi times h. Okay. All right. So now we're thinking, what are these things that that we want to add up? Okay. We want to take a look at a horizontal slice. So what I'm going to do, I'm try to draw this in here best I can, and that is I want to take a, come on, I'm trying to change the color. I want to take a cross section. I'm going to be wanting to add up all these cross sections. Sorry, my Surface Pro has decided it's time to ask me if I want to install some stuff to optimize my storage space. That's what the noise is, and slight distraction. I have dismissed that little thing. Okay, so I'm going to take a look at what the cross sections look like. I'm going to want to be adding up things going from in this direction like this, and what do those cross sections look like if I cut the cylinder horizontally? Those cross sections are rectangular, and they are sitting here like this. I'm just slicing it, and I'm taking a look. So that is one horizontal cross section there. So the area of that cross section. So I'm looking at the area of the, and this is the area. I'll just put it in words, right? Of the vertical cross section is equal to h times w. H is a constant. It's the same h as here. I'm not changing the meaning of the word h, the meaning of what I'm calling h. It's the same h, which is not known actually. We don't know what is h. So let me just make a note of that. H is not known. So we're just going to carry it around as h under the assumption that if we needed it at some point, we were told it, or maybe it will cancel out later. Okay, and then the width is a function of where we are, like where. So I've sort of drawn this arbitrary horizontal thing here, but I'm going to say that I'm going to measure x in this direction here, like this, x, and this area that we have here is a function of the width, which is this distance right here, W, and that is dependent on where we are in the tank. So that is a function of X. So I'm going to make a note to myself there. W is some function of X. I'm just going to get a few little endpoints so I can check my formula when I try to figure out how W changes as a function of X. I want to have some ones where I can see exactly what it is. And so I'm going to identify for myself what is W of 0. So what is the width when X is 0? So now I can imagine just a little strip of water right in the bottom of this tipped over cylinder, and that width is going to be 0. Okay, then another easy point to identify what the width of my rectangular cross section here would be at 5. So when the water in the tank was half full, the water would be that rectangle would be right along the diameter of the cylinder. So the width of the rectangles at when X is 5 is 10, and similarly the width at 10 will be exactly like the width at 0, it'll be 0. So whatever function I develop, if it's correct, it will for sure satisfy this criteria here. So now I have to figure that out, and now I'm going to take a look. I'm imagining taking a look at a cross section, and I'm looking at a vertical cross section. So it's a circle, and then I'm going to identify where that width is that I'm trying to figure out. So I have that circle. I'm going to draw this in a different color now. I'm going to have that circle here, like that. Okay, I know that, so I'm looking at that end, and that distance there is 10. That's the diameter of the cylinder, so that is 10 diameter. Okay, and I'm measuring X, some value here, X, right? That is what I'm choosing, X. So that is this X right here. It is sitting right here. I'm coming up from 0, and so my X is right here. So that means I know, actually, in fact, know this one as well. It's 5 minus X because the radius is 5. So 5 minus X plus X is 5. Okay, I draw a line here. That is actually, in fact, what I want. That is my W, that line I just drew right here. Okay, so I'm trying to get an expression for that. I am going to label this thing right here as R, like that. And I'm going to then be able to compute this guy right here. Well, I actually know what that is. That is 5, because that's the radius of the circle. That is 5, and that's going to allow me to compute R. So I know that R squared plus 5 minus X squared is 5 squared. Okay, so that is the Pythagorean theorem on this little triangle I've put here. So that tells me what is R. R is the square root of 25 minus 5 minus X squared. There we go. And that width I'm trying to calculate is 2 times R. 2 times R, that is this right here, which is the width of that rectangle. That is this width right here. So 2 times R is 2 times square root of 25 minus 5 minus X squared. So I'm now in a good position to set up the integral, and that is the volume that I'm trying to calculate. I'm going to integrate X going from 0 up to 7, because that is how high the water is in the tank. This is now I'm calculating the volume of the water. I've got the total capacity of the cylinder already calculated. Now I want to calculate the volume of the water, and that is going to be integrating that area slice as I move up. I'm going to be adding together all of these rectangles. That is going to fill that area, and that will give me the volume. So now I have an expression for A of x. That is the area of the vertical cross section, which is h times w. I've now calculated out what is w. It is this right here. Okay, so that volume is going to be the integral from 0 to 7 of that area slice, which is the width times the height, and I'm going to be integrating with respect to x. There it is. So now I've got an integral. The volume is 2h times the integral from 0 to 7 of the square root of 25 minus 5 minus x squared dx. It's a relatively thoughtful process to come up with this integral. Okay, now when you're doing these kind of things, it's always good to be able to check what you're doing. Let's imagine this upper limit. Okay, so imagine if I did this integral, 0 to 10. Yeah? What should I get for an answer? What would it mean if I was going from 0 to 10? I'm figuring out the volume of the water. That would mean the thing was full. That means water fills tank. We already know what the total capacity is. So if I were to do this integral, I would expect to get 25 pi times h. I already computed the complete capacity of the tank. So it allows me, when I go to compute this integral from 0 to 7, and I wonder if I have got this set up correctly, I can compute it from 0 to 10 and see that I would get this expected result. Always good to have something to help you check your work. So now the problem, if you were in an exam situation that said set up but do not evaluate the integral for finding the volume of the water, you would now be finished. We're supposed to evaluate this integral and then see what percentage that is of the total capacity, which we've already evaluated to be 25 pi h. So we can't stop. Okay, so now what? I'm thinking I want to see something. Okay, this is the next. Now I have a difficult integral to do as well. So really a whole lot easier just to tip the tank up, right, and measure the new height. But anyway, we're not in experimental physics. So I'm thinking I want to see something that looks like this. That is the closest that this thing looks to one of the ones on my trigonometric substitution table. I want to see that. So before I even do the trigonometric substitution, I have to do the regular type of substitution just to get there. Okay, so I'm going to do that first. So I'm trying to get my integrand to look like this. I see that I have something squared, but it's clearly not just a single variable squared. So I'm going to make this substitution. Let u be 5 minus x. That means that du will be minus dx. And then it's a definite integral, so I'm going to have to change the endpoints during the substitution. So when x is 0, u is 5, and when x is 7, u is minus 2. Okay, so now I'm going to rewrite the integral like this. This is substitute the endpoints of integration, completely substitute the integrand. Okay, and then just because it's a bookkeeping thing here, I see the negative sign here, and I'm going to reverse the order of integration and get rid of the minus sign. That will just make things less likely for me to make a mistake. Okay, there we go. Now it is of the form a squared minus u squared. right here. That is of the form a squared minus u squared. So then I go and make my inverse trig substitution. That was going to be u equals a sine theta, where a in this case is 5, because 5 is the square root of 25. So that is going to be then u is equal to 5 sine theta. And that means, of course, sine theta is u over 5. And du will be 5 cos theta d theta. On anticipation of needing the triangle, I am here. And the triangle is going to be theta u 5 and square root 25 minus u squared. Okay, I'm going to leave some of these steps, as I said in the beginning, to you, but let us now at least make, I'm at least going to make this substitution here, and I'm going to now have moved here. I'm making, well, let me do it this way. I haven't done anything yet. I'm just copying that down, du. Now I'm going to make the substitution. Okay, now, what do I do with the limits of integration? This is u equals, u equals minus 2. This is u equals 5. So I'm working under this substitution here. U equals 5 sine theta. So that means this is going to be here. Theta equals the arc sine of minus 2/5. And then the upper limit is going to be pi by 2. Okay, that is u is 5. Sine theta is 1, right? So when u is 5, sine theta is 1. And what angle gives you sine theta of 1? That is pi by 2. Okay, let's keep going with the substitution. That is going to be then 25 minus, and then we have u, 5 sine squared theta. Be careful here. 5 sine theta all squared. And then we have du, 5 cos theta d theta. All right, now we should be able to complete this whole thing. So we can make some simplifying algebra. So next step, some simplifying algebra. Then we're going to use the 1 minus sine squared theta equals cos squared theta identity change. And then we will, so there's some steps missing here, but that is the key, some algebra and using that identity there. Then just to give you an intermediate step, that should allow you to get to this. 25 times the integral, the arc sine of minus 2/5 up to pi by 2 of cos squared theta d theta. All right, so that is where we have been many times before. There it is, that cos squared theta again. So then that you proceed with the trig identity that we have been using for that, and that is cos squared theta is 1 plus cos 2 theta over 2. So you need that trigonometric identity. And then you can integrate this thing and evaluate it, and you should find that this volume comes out to be, well, one more step. This integral will come out to be 29.3615 approximately. And then that means our volume is 2h times this integral. So that becomes this here, 29.3615. And our percentage then used, the percentage used is then in fact equal to 2h times 29.3615 divided by 25 pi times h. So it actually doesn't matter. terms of the percentage used, what the length of that cylinder was, and then we multiply by 100 for the percentage, and we find out that it's 74.77% full. Okay, it's actually a fairly complicated calculation to figure out what a sort of a right cylinder on its side filled with water, to figure out how full it is at sort of an arbitrary location. Okay, a complicated example, bringing together actually a whole bunch of things that we've been doing. So take a bit of time and go through this. Maybe if you've looked at the solution and gone through it, then maybe wait a day or two, come back and try the problem yourself right from scratch, and see that you can generate all of it yourself. That is all for today. We'll be back with our final major technique in integrating, which will be integration by parts. Thank you. Bye.